So our second speaker is Gautam Sathichandran from Princeton, and he will talk about generalized black hole entropy and phenomenon algebras. Please.
So, can everyone hear me? Hello? Okay. Okay, so, right, so thanks for the invitation. So when speaking to such a diverse audience, it's sometimes very difficult to, pick a topic or something, but, really we're here to honor Edward's work. And as you'll basically see throughout this whole talk, all of this work is largely inspired by Edward's recent work. I've highlighted the two most relevant papers, but there are even more I haven't highlighted. And so this is work that I'll describe with that I did with Jonah Kudler-Flamm and Sam Leuthäuser at Princeton. And we're going to be talking about black holes. And so I think the first thing I need to go over is, what I've drawn here, which is a black hole spacetime, or a portion of a black hole spacetime. So what I mean is there's a stationary black hole where you know that because there's a killing vector, which is, this stationary killing vector, which is null on the horizon of the black hole. And I've drawn the portion of this. So this could be like, Sagittarius A star or something, it's just some black hole that's out there. And, I'm, at this time that I've drawn here, let's say is now, okay? And I'm giving my talk somewhere in the exterior of this black hole. And if I do a bad job, or you're not happy with, what I'm talking about or something, you could throw me into the interior of this black hole. This is the portion of the space-time that I would generally have access to. And despite my, gesticulations or me asking you not to throw me into the black hole, I will see effectively a stationary space-time for all intents and purposes in this, as I probe this interior and exterior region. So for everything that I see, I might as well pretend as though I see, effectively a black hole that has been around forever. This is maybe the more conventional diagram that you would have generally seen, where you can take this killing vector and extend it back, and at some point it'll vanish at this so-called bifurcation surface. So this is the point here where these horizons, where this future horizon and past horizon meet. It's really a sphere. Okay, so right, so this black hole, I'm thinking I got it from some gravitational collapse, and in particular any quantum state, and we'll be really talking about quantum states also in this talk, will also rapidly settle down to a stationary state, which we'll generally refer to as omega in this talk. And this is going to be stationary on some algebra, some observables, or some quantum fields in the exterior. And this state is necessarily mixed if on this algebra of observables in the exterior, due to the UV correlations across the horizon. So what do I mean by that? Well, if I'm considering, and just for definiteness in this whole talk, let's consider a massless scalar field. So if I consider such a field, if I look at the points, if I look at the 2-point function of the scalar field and bring the points very close together, well, that 2-point function, as all of you undoubtedly know, will diverge. Diverges like 1 over the geodesic distance. And in particular, if I look across the horizon, well, this divergence happens everywhere. It happens also at the horizon of the black hole. And this means that I have these, this operator is really strongly correlated when I look across this horizon here. Okay, so that's the origin of this mixedness of the quantum state. I refer to the algebra of these quantum fields. Well, in particular, what kinds of objects should you be thinking about? Well, phi of x, that object I showed you before, is actually not an element of such an algebra. You can't square it. I mean, if the origin of the fact that you can't square it is exactly here. If you bring the points together, you're going to get infinity. You really should smear this field in space and time. If you smear the object, then you can square it. So that's what this F is. It's, effectively smearing out this field or averaging this field in space and time. And I mean, I can't help but mention, because it's so relevant to the rest of this talk, that this is kind of overkill, this smearing in space and time if you wanted to get a well-defined element of the algebra. It's really, in fact, sufficient to merely smear the field in time in this, not very well-known paper by Borchers, where you could just integrate just the field in time, and the correlation functions of this field, or this observable, will be well-defined. Okay, so that's just a brief aside. Let's get back to black holes now. So I said there's this stationary state that really settles down in the exterior of the black hole, but it's not just stationary. Remarkably, it is also has, well, a thermal property, in the sense that, as Hawking showed, if you look at asymptotically late times at null infinity, what you will see is that the state becomes thermal. And since Hawking knew quite a bit about, black hole thermodynamics, he immediately realized that you should assign the entropy of the black hole to be the area over 4g Newton. Okay, and this immediately also suggests that the total entropy, the generalized entropy, is the sum of such quantities, the area of the black hole over 4g Newton, plus the entropy of the matter in the exterior of the black hole. Okay, so this is a very nice formula, let me just say, but if you stare at the formula for a long enough time, you'll start to get confused. Well, the first confusion is that this is all in the semi-classical limit, right, of negligible back reaction on the quantum on the background spacetime. I have quantum fields just propagating on a background geometry. So this is in this G Newton goes to 0 limit. Okay. Well, this first term diverges in this limit. And also in the semi-classical limit, I mean, I have quantum fields on this fixed geometry in the sharp horizon. The von Neumann entropy of the quantum fields in the exterior of the black hole will also diverge. However, it was argued over 30 years ago or so that, or more than that, that the sum of these two quantities might be better defined than their individual terms. Okay, so. Well, and the reason I'm giving this talk is because, remarkably, Edward and Roberto Longo and collaborators have shown that, the work with Longo was in de Sitter, which I'll get to later, but Edward and collaborators showed that, if you ask a completely different question, seemingly different question, you look at the algebra and the whole point of this talk is to explain to you what this means, of gravitationally dressed observables in the exterior of the black hole, and you compute their von Neumann entropy. Okay, so you consider this quantity in the exterior of, in particular, what was considered was a Schwarzschild ADS black hole. Well, this quantity is well defined. That's remarkable on its own because, I just told you, at least in quantum field theory, without taking any of these considerations into account, such a quantity would be infinite. Well, it's not only well-defined, but in a particular sense, it's equal to this generalized entropy that I gave you before. Okay, so you ask a different question and you get this result. Okay, so the whole point of this talk is to explain this last bullet point, and let's review first the case of the Schwarzschild ADS case. Okay, so this is a diagram of a black hole in ADS spacetime. It's ADS because it has a time-like boundary. So I've cut off this asymptotic region that I gave before, and now I have this time-like boundary here. And this black hole is sitting in the interior of the Schwarzschild ADS, and the exterior region is this region R that I've drawn for you. Okay, so in ADS, the black hole is, so I told you black holes radiate. If you have this time-like boundary set up, the radiation bounces off this time-like boundary here and really sets up a globally thermal state in this region, in this exterior region of the black hole. Okay, so what I am interested in, I'm interested in the algebra of quantum fields in the exterior of gravitationally dressed fields in the exterior of the black hole. Or I'm interested in explaining to you what that means. And in particular, that means that we're interested in we want to understand the diffeomorphisms of the theory and how they act on such fields. And the first problem we're going to run into is that the quantum fields themselves are not diffeomorphism invariant. Phi of x, phi averaged over some region of space-time are not diffeomorphic. They're not even time translation invariant. And so given a diffeomorphism, one can construct a gravitationally dressed observable, which we'll do in a second, a physical observable, by either dressing that observable to the boundary of the space-time or to another gravitating body. Okay, and we'll consider both cases throughout this talk. Okay, so how do we do this? Well, it follows basically from Einstein's equations. So if we consider the field, so we have some field propagating on this background space-time, and we consider this field as a first-order perturbation of this background geometry. Okay, so if it's a first-order perturbation, that means that it enters the stress energy tensor, which will enter into Einstein's equations, is a second-order quantity, and it's going to yield second-order perturbations of the gravitational field, which we need to quantize. Okay, so how would this enter? Well, I have my field. My field is a first-order perturbation, which means that the stress energy it's going to induce is a second-order perturbation of when it enters into Einstein's equations. If I ask what is the total energy of this field, which induces this perturbation of the geometry, well, this is this hc. I just integrate this stress energy over a Cauchy surface, and if I plug that into Einstein's equations, this total energy is equal to the difference of the perturbed second order. This is a second order mode of the gravitational field, the perturbed ADM mass of the right wedge, and the perturbed minus the perturbed ADM mass left. Okay, so that's the quantity I get if I plug that into Einstein's equations. Okay, so we have to include these degrees of freedom, or these modes of the gravitational field, in order to, well, impose this kind of relation. So this perturbed masses, the ADM masses on the right and the left, generate asymptotic time translations of the left and right wedges respectively. And so that's represented by these kind of bold symbols now, where now I want to think about including this as a quantum degree of freedom. So I'm going to bold such symbols. And so the relations they satisfy are written here. And since the perturbed mass takes any value on the real line, I mean, you can make the mass go down, or the perturbed mass relative to the background go up and down. You can quantize this mode and this mode on the Hilbert space of L2 of R, so square integrable functions allowing, of these masses in the right and the left. So now we've succeeded in quantizing this mode of the field, and this is really, well, physically what this is allowing is for fluctuations of the black hole mass at order g Newton. Okay, so, well, what's the impact on the quantum fields? Well, if this perturbed mass in the left lies in the commutant of the region that I'm interested in, okay, and so this algebra of the so-called dressed observables, which commute with this perturbed mass living in the left, is the one that commutes with, well, if it's the perturbed mass living in the left, that means it commutes with the generator of time translations of the fields plus this perturbed mass of the right on this Hilbert space. And so that's easy to write down. I mean, so what you do is you just construct this a so-called dressed observable. So what this observable is a quantum field. It's a joint field, a joint object of the quantum field dressed to the black hole mass in such a way that the field is conjugated on either side with this e to the I h c and t, where t is this kind of asymptotic time that I've shown you here, and I've suggestively written it in this kind of form. Okay. So, well, this is a new algebra. That's the first point. I mean, this is just a new object and the new algebra that you get from imposing this by promoting these guys to genuine modes and quantizing them. But so to more precisely explain to you what this algebra is, well, I need to take a brief detour into things that were discussed slightly in the last talk, which is this classification of algebras that was mentioned previously. So these algebras can be classified by their entanglement structure, and this slide is not going to do justice to the precise definitions, but I just want to get the point across. at least the necessary points required for this talk. So the first one is the case of type 3. Type 3 was the case that we were previously considering on the first slide, which is the canonical example is just local quantum field theory, as Stefan was pointing out at some point in his talk. And these algebras do not admit pure states. Every operator is going to be entangled in some sense with the operator in the commutant, and they don't admit density matrices. These correlations are far too strong to define a trace. Okay, so the other example is type 1. This is kind of the flip side of the coin. These admit pure states, they admit density matrices. A trace is well defined, and a canonical or a nice example to keep in mind is just global quantum field theory on a complete Cauchy slice. Okay, so what's an intermediate case? Well, it's intermediate in the sense of numbers, but also in its quality. So it does not, this case of type 2 does not admit pure states, but density matrices and entropy can be defined. So a trace can be defined up to a state-independent constant, which will appear in some of these formulas I'll write in a second. And if there, in the case, in some terminology, if there exists a maximum entropy state, then the algebra is called a type 2-1 algebra. And if there doesn't exist there's no maximum entropy state, this entropy is unbounded, then it's called type 2 infinity. Okay, and so what's an example of a type 2 algebra? Well, I claim the algebra of these dressed observables in the exterior of the black hole that we just considered is exactly an example. Well, if more precisely, if the state that we built this whole theory off of, this vacuum state in this region R, in the exterior, in this region that we're considering is thermal, then the algebra of these dressed observables is a type 2 algebra, von Neumann algebra, but I didn't need to say the word von Neumann, and I won't define that. You refer to Stefan's talk for more details. Okay, so that's the example, or that's the interesting thing. And what is going on here? Well, to give you a little bit more intuition, if a state on this new theory, the state of the quantum field together with fluctuations of the black hole, is a state of the quantum field tensor, I could pick a state of this type, tensor these fluctuations of the black hole mass, and this kind of joint observable here, this wave function of the black hole effectively smears out, in some sense, the quantum field, because now if I integrate in with this function of the black hole, I'm smearing out this operator in this extra mode, and this joint observable somehow becomes, which I won't be able to talk about in more detail. I suspect Edward will maybe talk about this to some degree in his talk. Effectively regulates things and makes things better defined. The key punchline is that indeed the von Neumann entropy of these algebras are well defined. You can compute them, and if you compute the von Neumann entropy of these so-called semi-classical states, so I just mentioned, if you allow me to go back, I just mentioned that this wave function of the black hole is effectively averaging the quantum field in time. So the correlation functions of these new observables are, nothing like the original quantum field observables. But if you average over sufficiently small amounts of time, you can recover, what look like your quantum field theory that you started out with. And indeed, the semi-classical states are precisely those states in which this f tilde function, this function of time, is sharply peaked. And in that context, you can recover precisely that the von Neumann entropy of this semi-classical state is, the generalized entropy that I gave you before, up to this fluctuation term. This fluctuation term, if f was a Gaussian, is just proportional to the width of the Gaussian. So it's some kind of fluctuation entropy tied to the black hole and up to an arbitrary constant. And indeed, the algebra is, type 2 infinity, and that should be intuitively obvious because this mass, this ADM mass of the black hole is unbounded from above. So you can increase the entropy arbitrarily. Okay, so, that was the case that was previously considered. And let me just do another case that was previously considered, which was the case of de Sitter spacetime, which was also analyzed by Longo, who's in the audience as well. So the case of de Sitter spacetime, well, this diagram might look very similar, but it's completely different. So this de Sitter spacetime is a closed universe. And what is going on here is I've drawn an inertial observer. This inertial observer has a domain of dependence, which is this region R, which is as I've drawn here. And there's an associated kind of killing horizon associated to this observer. And this infinity here, the scribe plus, is the cosmological infinity now, outside of this cosmological horizon of the observer. Okay. And the key, well, what is the quantum state that we would need to consider in this case? Well, it's the so-called Bunch-Davies vacuum, which has an analogous property to the case that we considered before, in the sense that if I restrict it to this region R, it is thermal in this right wedge. Okay, so what's different about this case, and why is it not immediately obvious what to do? Well, de Sitter spacetime is closed. So if you impose Einstein's equations, the total energy, when you integrate over a Cauchy slice, is indeed equivalent to some boundary terms, but in a universe without a boundary, that means that the total energy must vanish. And so this, if you impose this constraint, will yield a trivial algebra, because the only operator that commutes with the generator of time translations is the identity. So in order to obtain a non-trivial algebra, we need to basically break this degeneracy. So we need to introduce another gravitating body. And the simplest case or example considered in this work was to just introduce some kind of endow this observer with a clock with some energy, epsilon, and conjugate time, tau. Okay. And well, if you do this, then what are you doing? Well, you're basically, when I integrate this, again applying the same thing. Well, now I find that the sum of this quantum field, the generator of time translations, plus the energy of the observer, is now constrained to vanish. Okay, and you apply the same gravitational constraints as I was applying before, yields, well, the algebra of gravitationally dressed observables. Now I'm dressing to the this observer in the bulk of the spacetime is of the same character. I mean, this should look now kind of familiar to you, where now what's replaced by this time that we had before at infinity is now the proper time of the observer world line. And this algebra yields an algebra of dressed observables in exactly the same manner as before. But now that instead of perturbing off of some background quantity, I am adding this degree of freedom in by hand. It is physically reasonable to impose some bound on the energy of this observer that I've imposed, just put in the space-time. And if you then project onto the positive energy, require that the observer has positive energy, well, this is the algebra then that you obtain. And if you put any energy into the space-time, you shrink the cosmological horizon. So if the energy of the observer is bounded from below, that means that the horizon area is bounded from above. And that means that, it turns out to imply directly that the algebra has a maximum entropy state and is a type 2-1 algebra, and the entropy of semi-classical states is indeed, again, the generalized entropy. Okay. So now let's consider a case that is not covered by the previous analysis. So, in this particular case, we'll consider an asymptotically flat space-time, but we're going to consider, for this particular talk, the analysis is completely general, but for this particular talk, we'll actually restrict to a Schwarzschild black hole, asymptotically flat. Okay, and the first thing I need to point out is that this state, so the state, which is referred to as the Unruh state, the stationary state defined in the exterior and interior of the black hole, well, this black hole is not in thermal equilibrium. It's radiating out into empty space. So this omega, it is thermal way up here at asymptotically late times, but it is not thermal globally in the right wedge. Okay. So nevertheless, we can just proceed. I mean, there's nothing stopping us from continuing. And Einstein's equations relates the energy of the field, again, to the difference of the ADM mass at infinity and the perturbed area of the black hole. Okay, so in particular, I can consider a Cauchy surface of the following form. And if I integrate the energy of the quantum fields on this surface, so that's what's denoted by this hc here, well, I get, by Einstein's equations, just as in all the other cases we've considered, we get the sum of two boundary terms. The first boundary term is just the perturbed ADM mass in the right wedge, which we'll need to quantize just as before. And the second one is basically an area that we get here. So in order, well, this formula will appear a couple other times in the talk, so let me just tell you what it is more precisely. So if I looked at a finite, so if u is the affine, u in this formula here is the affine time on this past horizon. And at a particular affine time, you can look at the charge associated to this killing vector, xi, and it's equal to this perturbed area that you of the black hole or of this horizon up to this extra corrector term. And there's there's legitimate interest to look at this quantity on its own, but I'm taking this limit as u goes to infinity, and to go to the end of this surface. And in that case, if the space-time, the horizon settles down, and this term here, which is roughly speaking the derivative of the area, I mean that's the rate of change of the area. So if the horizon settles down, then this delta q here is just simply the perturbed area at the very end. Okay. So that's the relation that you get from Einstein's equations. And then what you do, well, you do exactly what I was telling you about before. Well, you have this extra mode of the gravitational field that you need to quantize. You do quantize it, and you obtain an algebra of dressed observables. Again, now dressed in this following manner. This should now look almost, I'm just kind of copy and pasting the formulas with relevant replacements of these different symbols, but it's exactly the same. However, the key thing is that the black hole is not in equilibrium. So one cannot directly, by just staring at this expression or the algebra of these dressed observables, determine the type of this algebra from anything that I've told you previously. However, to determine its type, it's useful to re-express the original quantum field. So we're dressing this quantum field here. It's useful to re-express this algebra of quantum fields in terms of initial data. Okay, so what do I mean by that? Well, if you give me any local observable of the quantum field, I can just propagate it back. There's nothing stopping me from doing it. It satisfies some local equations of motion, so I'll propagate it back to the asymptotic boundary. And if I propagate this observable back to the asymptotic boundary, this observable basically either falls into the past horizon or goes to infinity. Okay. And so what you can show is that, this is a non-trivial statement because there are null geodesics, of course, that just, never hit infinity. They just go around the sphere, the black hole forever. But you can show that there's sufficient decay in such a manner that either the observable falls into the past horizon or goes to infinity. And in case of a massless scalar field, you get no contribution at I minus. And indeed, the algebra factorizes into an algebra of observables on the past horizon and an algebra of observables at scry. Okay, this seems like some cute thing. It doesn't really look totally useful, except for the fact that, if you look at this omega, this Unruh state that I was showing you before, the stationary state, and you propagate that state back to the boundary, the state at scry is the vacuum state. It's just the standard vacuum state that you would have defined at infinity. And this state is pure. This is just a pure state living here. But if you propagate this state, it's exactly thermal on this. It's not thermal anywhere else. The state is not thermal anywhere else in the bulk, but if you propagate it back to the boundary, it's exactly thermal on this boundary. And indeed, it had to be thermal on this boundary because when you propagate these modes to the future, this thermality is what eventually becomes the Hawking radiation at infinity. So this thermality is in some sense intrinsic to the presence of the black hole itself. Okay, so what does that mean? It directly follows that the algebra, so what we did was we factored this algebra into the product of two algebras we understand better. And indeed, the algebra now, if you then take this dressed algebra that I gave you here and propagate it back to the boundary, you immediately see that this algebra is type 2, infinity, in fact. And the algebra here at Scry, well, I told you this state is pure. So this algebra initially that we had at Scry was type 1. And further dressing does not change this fact, because further dressing the entropies were defined to begin with on this algebra, and further dressing does not change the fact that entropies are well defined. So indeed, the algebra of observables in the exterior of the black hole is opaque in terms of its type in this thing, but when you write it in this way, is precisely the product of a type 2 algebra and a type 1, and therefore is a type 2 infinity algebra. And therefore the trace on this algebra is perfectly well defined, and one can compute the entropy of semi-classical states, and the von Neumann entropy is indeed the generalized entropy. Okay, and in my, well, I'm not sure how much time I have left, but let's do the last slide anyway. So let's consider the case of Schwarzschild de Sitter, another example that does not immediately follow from the previous work, which is, so this is a Schwarzschild de Sitter spacetime. You can see that from the fact that this is the black hole. Yeah, hopefully that's clear from this scary place that we're not going to talk about in this talk, but this is the black hole region. This is the exterior of the black hole. So this is the horizon. This is the past horizon of the black hole. This is the exterior. This is the past cosmological horizon. And this is the future cosmological horizon. And this is the infinity. And we're interested again in this region, intervening region between the two horizons. Okay, and why this case is also slightly non-trivial, because the algebra, there is a perfectly well-defined stationary state, but when you propagate it back, it's thermal, again, on this past horizon of the black hole with inverse temperature, beta 1, so it has some temperature associated to the black hole. And this state here will be thermal, or the horizon will be thermal, cosmological horizon will be thermal with respect to a completely different temperature in general. Okay, so the fact that these temperatures are not equal means that the omega, the vacuum state that we're going to get in the intervening region will not be have this thermal character. Okay, but indeed, you can, when you propagate the observables back, you find that the algebra of observables factorizes in this following way, and that's going to be fairly crucial for understanding what the algebra of the dressed observables are. Okay, so as opposed to the previous, but there's one further caveat that we need to consider, which is, as opposed to the previously considered cases, that both boundary charges will lie in the commutant of the algebra. So I'll show you that in a second. So the algebra of gravitational constraints will again yield a trivial algebra. So let's see that. So if I now take a Cauchy surface for this spacetime, okay, and I now impose Einstein's equations, now we're all experts. We know exactly what's going to happen. If I take the energy evaluated on this Cauchy surface, it's going to become the difference of two boundary charges, or I guess sum of two boundary charges living here and here, which are basically the areas of the black hole, perturbed areas of the black hole and the cosmological horizon living at either end. But both now live in the commutant. So the problem there is that, this means that the constraint that I'm going to get is that all the algebra elements that I'm interested in must commute with the generator of time translations just as before, and we run into the same problem that we had in de Sitter spacetime. Okay, but that's not so hard. Let's just follow our nose as in the de Sitter case and add an extra gravitating body. Okay, this observer that I showed you before, and I've depicted it here as some object that just is living in the space-time. Its energy now breaks this kind of degeneracy, and now I get that the algebra must commute with the sum of these two guys, just as before. So it would appear, I've made it seem so hopefully it does appear, that the gravitational constraints are identical to the de Sitter case. Okay. However, we have two physical, we have the black hole, a physical body in the space-time, as well as the horizon, the cosmological horizon. And the areas of those horizons can independently fluctuate. And looking at the fluctuations of the black hole horizon as well as the cosmological horizon will yield, in the next slide, we'll see this explicitly, yield stronger constraints on the algebra than the ones I've shown you so far. So let me show that. So what I've done here is split up this formula into the sum of 3 contributions. One on this horizon, one coming from here, from this incoming observer, and one coming here. So that's what this thing is, and I'll just talk you through it step by step. So this, I'm evaluating this energy flux just through this piece here. Remember, the algebra is factorized, so I can do this independently on this guy and this guy. So I'm going to now consider the flux just on this surface here, and that's the difference of 2 boundary charges. One living, again, way up here, and one, being this perturbed charge in the asymptotic past. Again, we get the same story for the cosmological horizon. We get this energy flux of the cosmological horizon through the cosmological horizon is equal to the difference of these perturbed charges, one far in the future and one far in the past. And again, now, well, this energy, this incoming observer energy, perturbs the areas. Now the sum of the areas of the black hole horizon and the cosmological horizon satisfying this relation. Okay, if you add these formulas up together, you get back this formula. Okay, but now this imposes a constraint on the algebra of observables just living on this past horizon here. This formula imposes a constraint on the algebra of observables living on the past horizon here. And this constraint, well, it's not really a constraint at all because I can choose the observer as I want, but we're going to impose positivity of the observer energy in a second. So that's going to give a slight constraint on that. Okay, so if we the punchline is that if we quantize the perturbed area of the black hole and the perturbed area of the cosmological horizon, okay, so we allow for independent fluctuations of these at order G Newton, and the constraints imply that the first constraint, the one we get from this term here, is that the algebra of observables just living on the past horizon is type 2 infinity. Now, if we then look at the constraints applied to the algebra of observables living on the past horizon of the cosmological horizon, we get that the algebra of observables are again type 2 infinity. So that means that it's the algebra of dressed observables is the tensor product of the algebra of observables living on both horizons just as before. And then what we then have to demand is positivity of this observer energy as a physical requirement of the theory. So that means that, well, if the energy is positive, that means the sum of these 2 perturbed areas must be negative. And so this means that this constrains the sum. However, that means that we still have an unbounded mode of the theory, which is this difference of the areas. And this unbounded mode turns out to imply that the von Neumann entropy is still unbounded from above. So it implies that the algebra of dressed observables is actually type 2 infinity. So, and indeed, the von Neumann entropy of semi-classical states, one can just directly compute, is exactly, again, equivalent to the generalized entropy, again, up to this fluctuation term. Okay, so I think now I better wrap up, and let me just say, I guess I could go on and say much more things, but let me just say at least the last 2 points. The first is, well, I gave you a couple examples, but this story that I've just explained to you holds in kind of full generality. So the generalized black hole entropy for any stationary black hole in the exterior, if I'm looking at the exterior in the gravitationally dressed observables, is the von Neumann entropy of the algebra of the gravitationally dressed observables in the exterior of the black hole. And really, more generally, these results suggest a very deep connection, I believe, and to me at least, completely unexpected, between the physical observables in quantum gravity, even in this perturbative sense, and the generalized black hole entropy. And I think it would be very interesting to explore these connections further. Let me end there.
Thanks a lot for this nice presentation. Questions? There's maybe time for 1 or 2 questions.
Sorry. You know what parts of this story continue to work if you didn't assume stationarity of the background?
I use the killing vector.
Right.
So yeah, it's a good question. Yeah, so one, well, can I rephrase the question a little? I mean, you could even just, yeah, because I don't know, is basically, but you could even ask, I was looking at the algebra of observables. Let me go to a picture that's better suited for this question. So algebra observables in the full exterior of the black hole. One could ask about kind of a dynamical black hole entropy, where I'm just, even in this perturbative language, looking at arbitrary horizon cuts and, throwing things in. And then the algebra, the diffeomorphisms that preserve a horizon cut will not be this background isometry. I think that's an extremely interesting question, and I don't. The kind of general problem here is that these algebras of these gravitationally addressed observables don't obviously satisfy this inclusion that was so useful in the original formulation of the GSL. So even in this kind of more concrete version of your question, I mean, not that your question wasn't concrete, but slightly, I could even draw this picture or whatever. I don't know how to analyze that, but I think it's a very interesting question. Yeah.
You had in one figure you had a surface that went all the way off to that upper corner.
Yeah.
Usually that's covered up by the star.
Yes.
So it's not. What would you say?
Yeah, so I was making the approximation where, well, yes, this whole past horizon should be covered up by the star. So as I was trying to explain in the beginning, if you look at, well, let's see where here. So the idealization that is made, I mean, so the best answer to your question is the answer to Jaffer's question before, right? Which is that you look at a horizon cut that is to the future of the bifurcation. So, but so this is where one should do physics. Okay, here. I mean, this is where, I said this is Sagittarius A star, and this is now, right? But unfortunately, I mean, the technology that I presented is better adapted, basically, to the situation where so Sagittarius A star collapsed 2 billion years ago, something like this. So we're extremely far to the future, and you kind of idealize this collapsed star to be basically flattened, and so in some sense, so it really, you can take this Cauchy surface and take it, really, really close to the bifurcation surface, and this is the approximation I'm in, basically. But so this is I'm ignoring the subtlety of the fact that I really shouldn't be right through the bifurcation. I mean, I should, this is more of an idealization, just as much as this picture is an idealization that we use for physics. But yes.
Okay, maybe final question and a quick answer.
Thank you for the nice talk. You said when you have pure de Sitter, basically, and you have an observer in there, then you have the cosmological horizon. If the observer has positive energy epsilon, that subtracts from the horizon, basically entropy, and so it's bounded from above. Now, if you have Schwarzschild de Sitter, which you had there, then there is no bound, basically. There's no, but there is this what is called the Nariai solution. Where if you give your de Sitter with CC, you cannot have a black hole of arbitrarily high mass, and therefore, so then the total sum of entropy seems bounded. How do you see that here?
Yeah, well, Edward, did you want to say? Yeah, okay.
In this approximation,
oh, there's a microphone here. Yeah.
there's an upper bound on the mass of a black hole in de Sitter space, but in this kind of approximation, you can't see it because order 1 fluctuations rather than order 1 over G fluctuations are part of the story. So I could have let you answer.
No, that exactly is what I would have said, and you probably said it better than I could
Very
have said
good.
it.
And it followed my constraint to be a short answer.
Yeah.
Very good. Okay, so let's thank Gautam again.